Greetings and salutations unto the Matric AP students, and we are looking at today the explanation of volumes of solid of revolution formula. So you're going to need that worksheet, which is on Teams. I also WhatsApped it to you. Just share the screen. Okay. So, first of all, what's happening here is, if you can imagine, we're forming a 3D shape, a solid of revolution. And what we do is we take this curve over here, okay, and if you can imagine that every time that wherever the line goes, we rotate it about the x-axis. And as we rotate it, imagine that's becoming a solid. Okay, so everywhere the line goes, it's kind of closing up as a solid, and you get this hollow shape. Okay, and but the central pivot, okay, the central pivot is this line over here, right? So what happens is you end up with a solid, if you imagine that's your central pivot over there, okay, and you've taken this curve, okay, and you've rotated it about the x-axis, and every time, as I say, everywhere it moves, it forms a solid, and you get this hollow solid, okay? So this would look like a kind of a vase, I guess, a solid vase, okay, where that would be the bottom over here, that's that bottom over here, okay? And if you imagine looking down on it, then you're looking from the perspective of the x-axis, and you get this hollow solid. It looks like some kind of a vase, clay pot or something like that. That's your base. This over here would be your front would be formed like that. Okay, so there's your front formed by rotating it. So for the syllabus, we focus on volumes of solids of revolutions formed by rotating about the x-axis, just because generally the functions we work with are functions of x, not functions of y. Okay, but there's no reason, I'll show you on the next page, why you couldn't form volumes of solids of revolution by rotating about the y-axis. Okay. So your key ideas for me in the proof of this is, well, we're kind of using similar principles to finding the area that when we use the Riemann sum. And when we use the Riemann sum, okay, we added up, instead of adding up rectangles to get area under the curve, we're adding up volumes of little tiny individual disks. Okay, so if you can imagine, okay, that you've got a disk, it's parallel to this shape over here, you've got disks formed, okay, my diagram's not very good, you've got disks formed, and in each disk, okay, where previously your width, in Riemann sums, that kind of width that we had, which was b minus a over n, okay, that was the width of each rectangle. Now what we're going to think of that as being this width, okay, the width of each cylinder or disk. This is the width of each cylinder or disk, okay, and that little width, that bit over there, is your change of x. Remember, dx means a very small, the notation dx means a very small change of x. So your height, you want to think, if I've taken that cylinder now and moved it across like this, your height, I tried to do a vertical one, I wasn't very good at it. Your height is dx. This distance over here, that distance is dx. So that's your change of x, right? So if you're imagining you're dividing this whole shape up into, instead of now adding up areas of rectangles, which we did with a Riemann sum like that, just looking above the x-axis, now we're adding up, we're making an infinite number of volumes of disks, okay? So each disk, we see the disks by looking down on it over here. There's a disk, okay, you can really see the disks, each disk, okay? Now, so each disk has a height, okay, this is your height of dx, okay? The radius of each disk is that distance over there that goes up to the curve. Sorry, if my curve went up to there. That's your radius there, right? So that's your radius. If I look at this over here, this is my radius over here. So this is your radius of each disk. So that's your radius. And what is your radius? Well, your radius is the y value. If I looked at this point xi, that point over here would be f of xi. Okay. So the distance from there to there is f of xi. Okay. We rotate it, but that distance stays the same. We take the absolute value, if you like. Well, it will always be positive if it's above the curve. Okay. So this radius is f of xi. Okay. So the width is the height, the width of each rectangle there, sort of, okay, is the height of each disk. So there's your width. Your width is dx, change in x. Okay, tiny change in x, dx. Okay, your radius is f of xi. Okay, the point on this function. So if this was x over here, your radius would change. Your radius is not fixed. Okay, dx is fixed because it's infinitely small. That would be your radius over there in that case. It would be smaller. Here it would be bigger. Your radius is constantly changing, but the radius is the y value on this curve. In other words, f of xi. So if I look at the volume of one disk, okay, the volume of a disk or a cylinder, we know, is pi r squared, area of your base, times your height. But in this case, your radius is f of xi. Okay, and your height is your change in x value over there. So your height is dx. So that's the volume of one cylinder. Pi f of x dx, right? Okay, f of x, and that should be squared because it's pi r squared. Okay, your height is dx. Okay, so that's for one disk. What is its volume made up of? Well, it's a sum, okay, of an infinite number of disks in that region. So the volume of your solid of rotation is the infinite sum of volumes of disks, right? And so remember from Riemann sums, this kind of idea, we can think of an integral, the integral of f of x, as the infinite sum. In other words, as the limit as n tends to infinity from I is equal to 1 to n of f of xi. That's kind of what we can think, one way of thinking about what an integral is. That's what the fundamental theorem of calculus says, is that a volume is a infinite limit, infinite limit sum is the integral. So in order to find the volume, we want to find the infinite sum of the volumes of disks, okay, of each disk, if you want to say. And each disk has a volume, so we're adding up. We want to make gaps infinitely small. Okay, remember, the more disks that you have, okay, the more accurate your volume for your solid. That's why we find a limit to infinity. From I is equal to 1 to n, your formula for the volume of a disk is pi f of x, which is going to f of xi, okay, squared. That's that bit over there. Okay, dx. Okay, but now we can say, we can express the infinite limit. We know that an infinite limit is the integral, okay, between, in the region we're working with. So it's the integral between a and b of pi. Okay, and now we drop the xi notation and just refer to it as f of x squared, okay, with respect to x, right? So there's our f of x squared with respect to x. So this is where our formula comes from. Remember, with integration, sorry, I dropped that. So annoying. Okay, sorry, I said the limit as n tends to infinity, the infinite sum of the volumes of each disk is the limit as n tends to infinity. Add up all of this from I is equal to 1 to n, okay, of pi f of xi squared dx. Okay, we drop the xi notation there once we move over to integral notation. So it's the integral just like we did with Riemann sum. Integral from a to b of pi f of x squared with respect to x. Okay, but with integration, the variable is x, so we can take out pi, which is just a constant, and I'm left with f of x squared dx. So this is your formula for the volume of a solid of revolution, which is formed by rotating some curve f about the x-axis. So we form the solid by rotating F about the x-axis. A represents, in your formula, A is your lower boundary. Okay, A is your lower boundary of your x values. Okay, B is your upper boundary of your x values. Okay, so this is your formula on your information sheet for the volumes of the solid of revolution. Okay, so what's the key ideas behind this? Okay, the formula, similar to a Riemann sum. Okay, you're adding up. Okay, you first of all, you breaking the volume up. You form the solid by rotating about the x-axis. Okay, then you break it up into all of these little discs. Okay, the width of each disk is your change of x, which is dx. We make that infinitely small. Dx means very small. The radius of each different disk will correspond to the y value on this curve. So your radius is f of xi. Okay. The volume of one disk is pi r squared h. Okay. In other words, your radius pi f of xi squared dx. Then to find the volume, a volume is the infinite sum of all of those volumes of each disk. Okay. In other words, the limit as n tends to infinity, you add them all up. That just means get as many as possible as you can in there. Okay. That's the formula for the volume of each cylinder. Okay. Which gives us, remember, an infinite sum is an integral in the bounded region. Okay. And that gives us our formula for the volume of the solid of revolution. So that's kind of what the syllabus looks at. Okay, working them out is not so easy. You're going to generally just use your calculator. It's not so difficult. You're going to just generally use your calculator. Now, this is not strictly speaking in the syllabus. Okay, but one year they did do an application question in an exam. But there's no reason why a volume of solid of revolution couldn't be formed by rotating about the y-axis. So now, if you can imagine your solid, to see the solid, you'd have to stand above there and look down on this thing over there, and there would be each disk. Okay. Now, first of all, your A and B would now be your y, your upper boundary, lower boundary in terms of y values. So A would be in line with that. Your shape would look like this in this case, if you can imagine. This is a cross section. Okay. But if you look down on it, okay, you'd end up with a cone. It looks like this. A cone which is made up of an infinite number of disks. Okay, a whole lot of disks would make up that cone. Okay, the one thing you'd have to do is you'd have to, if we took this as your function, you'd have to write this function as x is equal to f of y. Okay, so you get your x values here. Okay, there will be f of y. Now your height would be your change of y value, a little change of y value. That would be your height of each disk. So your height would be equal to dy, which just means a very small change of y, the height of each cylinder. Okay, and your radius would be that distance across over there, which would be f of yi. In other words, your x coordinate, how far you moved across. That would be your radius of each single disk. So if we looked at the volume would be pi r squared h, but your radius now would be f of yi with respect to y, f of yi squared, because your radius squared is f of yi squared. Your height would be dy. Stick to that color. Okay. So your volume would be the infinite sum of all of those individual cylinders, and the way we write an infinite sum is the integral in the bounded region in A and B of pi f of y squared with respect to y. You can remove the pi, and it will be the integral between A and B, where A is your lower boundary, B is your upper boundary, of f of y squared with respect to y. Okay, but that's not really in the syllabus. Okay, strictly speaking, the main part in the syllabus is this whole thing over here, okay, which gives us this formula that we're going to use. Volume is equal to the integral between a pi integral between b of f of x squared. Just don't forget to do the square when you use it. A lot of people forget that with respect to x. Righty, so that is an explanation, if it made some kind of sense, of the volumes of revolution. Okay, arrivederci.